Dr. Jill Tarter is a former director of the Center for SETI Research and the holder of the Bernard M. Oliver Chair for SETI at the SETI Institute. Jill was fascinated with the night sky as a teenager. She graduated with distinction from engineering physics at Cornell, a program that has produced a remarkable number of brilliant scientists, engineers, and I would like to say particularly radio astronomers. Frank Drake, Carl Hylas, Don Backer, Dave Kaplan come to my mind. In fact, I'll blindly accept any student from this program to work with me. Jill's 1975 UC Berkeley thesis was titled Interaction of Gas and Galaxies with Galaxy Clusters. It was centered around radio astronomy. Towards the end of her thesis, she coined the term brown dwarfs for substellar objects with the statement, brown is not a color, and thereby replaced the older name of black stars. Jill, having gotten bit by the SETI bug, thanks to Stuart Boyer, changed her focus to SETI, which is related to the topic of today's talk. Jill started her first big project on Serendip, was the project scientist for NASA's major HRMS project, and played a big role in setting up the SETI Institute and the very vibrant radio SETI program at UC Berkeley and Hat Creek, which still continues today. Her pioneering start and sustained devotion to SETI has made Jill as the most recognizable public face for SETI. In fact, in the blockbuster movie Contact, the primary character, Ellie Arroway, who's played by Jodie Foster, was in fact based on Jill. Only a few scientists reach a position where they comfortably straddle the academic, the research, and the ordinary world and shine in all of them. Jill, the stage is yours.
So with the recent kerfuffle about BLC-1 being leaked to the press and looking forward to a project called Cosmic, which I'll get to in a bit, at the VLA, it seemed to me that it was really time to be thinking more about Carl Sagan's directive that incredible claims demand incredible evidence, and what is incredible or credible evidence, and how can we best proceed with this search for either biosignatures or technosignatures in a way that helps us have as much credibility as possible. So I'd really like to talk about what the SETI community has been thinking about for quite some time, and not claim to have all the answers, but we have some things that we ought to be thinking about. So let's get into it. Back in the 80s, under the auspices of the International Academy of Astronautics and the International Institute of Space Law, the IAA had a standing permanent SETI committee. And we began to formulate something that we called Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. And you can see the lawyers there. And we did this because it made good sense programmatically, but also because this was a middle of the Cold War. And our Russian colleagues were doing a lot of SETI observations. And we were afraid that if they were ever successful, they would be prohibited from telling the world. And so we tried to put together these principles to give a little cover for them and a little backbone should they succeed. So what are these principles? They can be found here as a PDF. It's not a treaty. There's no enforcement possible. It's purely voluntary scientific cooperation and collaboration. And here they are. There are 9 principles, and I certainly don't expect you to read them, but let me summarize. Attempt to verify yourself if you've made a discovery. Ask your colleagues for help, an independent verification. Send an IAU telegram, and you're doing this to prime specialists around the world who can then be informed and deal with their local media when indeed you decide to tell the world, as you should. You need to publish any discovery data so others can look at it, find your mistakes, find other things. And you want to continue to monitor and record data from the source. If it's a radio signal that you found, you might want to ask the ITU, International Telecommunications Union, for some extraordinary protection of that part of the spectrum so that you won't lose data. And this is an important one, don't reply without some global consensus on who will speak for Earth and what they should say. And then speaking as the IAA Permanent SETI Committee, we said we'd like, as much as possible, to try and keep control and steer the what comes next to be the most reasonable. That one is really iffy. All right, so do this and you get to drink your champagne. So in addition, now in the current day of philanthropically funded technosignature searches, you need to fit in there before you tell the world, you discreetly tell your donors. So attempt to verify yourself. How does this work? So all current SETI searches are sort of invoking the uncertainty principle. The time bandwidth product of a signal cannot exceed unity. So that means that's if it gets close to unity, then we can distinguish engineering from astrophysics. So we look for frequency compression in the radio. We look for continuous wave or frequency compressed pulses, and we look for time compression in the optical. So broadband optical pulses or monochromatic lasers. And it's pretty easy to distinguish astrophysics from technology. So we're showing on the top panel a saturated OH maser, one of the narrowest spectral features that we found on the sky. And yet when you compare that with our technology, for example, the transmissions from a spacecraft, you can see that the sidebands are far narrower than the narrowest astrophysical source. And even when you blow that up more, you can look at the information being transmitted in the sidebands in a very narrow frequency domain. So we built detectors and we use them to look far away. This is the signal from the Pioneer 10 spacecraft while it was still operating. There's only 3 watts in that signal transmitted. It's 6 billion miles away, and it's hugely detectable in our instrumentation. So when you're looking for narrowband signals, there's another trick that you can do, which is to use 2 widely separated antennas on the planet, which is rotating, and then you can precisely predict the different Doppler shift and Doppler drift rates for these 2 antennas looking the same direction on the sky. And this turns out to be a really good way to discriminate against interference. So before we built the ATA, we did a bunch of SETI. We called it Project Phoenix, and it at the time was the most sensitive search that had been made. Of course, now Breakthrough Listen is improving on this enormously. Our observations were spread over 9 years, total of 482 days of observing, frequency coverage 1.2 to 3 gigahertz with a frequency resolution of 1 hertz. And we looked at about 800 stars within 250 light years. And we pioneered this concept of commensal observation. So here's an early image of M31 made by the Allen Telescope Array. And we used various catalogs to find interesting targets for SETI observations within that field of view. And at the time we were postulating we'd be able to build 8 dual polarization array beams within that field of view. Turns out we actually only got 3 done. It's harder than we thought. So we conducted this project called SETI on the ATA. We had a large field of view on the sky because the antennas in that array are 6 meters in diameter. So large field of view and 3 phased up beams within that field of view. And we observed 3 different targets at the same frequency at the same time. And then a signal that came from 2 or 3 of the beams simultaneously was terrestrial interference. Interesting signal was one that came from only 1 of the 3 beams. And in the next generation of backends that are being constructed, it looks like there'll be more than something like 64 beams will be what we can manage. So ask your colleagues for help. This is really get an independent verification with software you didn't write and hardware you didn't build. So what's needed? Well, a comparable radio or optical telescope. Size matters, but perhaps not as much as you might think. And so your confirming telescope can be smaller because you're actually telling someone exactly where to look in frequency and what pattern to be sensitive to. And so you can dig in with a higher false alarm rate into the data that comes from a smaller telescope. You need receivers that cover the frequencies where you've made your discovery. And you need backends that are sensitive to the particular type of signal you're looking for. Now, in the radio, since you've already made a discovery of a particular type of signal, particular pattern in frequency and time, you can probably get away with not having a fancy breakthrough listen or some other SETI backend. When someone tells you what to look for, you'll probably be able to get away with your commercial spectrum analyzers or your normal radio astronomy filters. But if it's in the optical, right, that's harder because you really need fast photon counters. And they're not necessarily ubiquitous at optical telescopes. So you may have a harder time finding a secondary site that can give you verification and validation. And of course, you'd like your second site to be west of your discovery site so you can keep taking data and analyzing it longer. So thinking about this project that's coming up that's being led by Andrew Simeon called Cosmic, it's actually going to provide for a copy of the voltages out of each of the 27 antennas at the VLA. And while the WIDAR correlator feeds data and makes images as usual for the astronomical observations, these copies of the voltages can be put into a special SETI signal processor, a modern digital correlator beamformer. And they can be searched in that domain for engineered signals. And so I think this is really, for the SETI community, this is really, really exciting because, you know, the VLA is really the most productive radio telescope on the planet. And to be able to be on the sky 24/7 in a commensal mode with the VLA is a real wonderful opportunity for our community. I'm looking forward to this. It's been slightly delayed by COVID, as has everything else, but Andrew is charging ahead, and I think that's great. So, all right, you're going to tell the world, and you got to be really thoughtful about how you do that. You need to prepare a press kit, and you'd like to have some really simple metric for informing the media and the public about the importance and validity of the signal you've detected. So we started working on that back in 2000, and we're using the Richter scale as our model, right? And everybody knows about the Richter scale, but we formed something we called the Rio scale because the first paper was presented in a meeting in Rio de Janeiro. And it's a numerical scale that runs from 0 to 10, and it tries to capture, there are two components that are multiplied together, and they try and capture both the significance of the detection, the reported detection, and its credibility. So it's 2000. We've been working on this for a while, right? And it's very hard because we don't have signals detected all the time. It's really very hard to know how well we captured what we wanted to. So actually, we used science fiction movies as test case for this scale. And right, over the next 2 decades, not a lot of traction. Not many people could tell you what the Rio scale is. But in 2016, right, it became incredibly important to have that tool to see how well it worked. Because in 2016, there were numerous announcements of discoveries of technosignatures, and the media went wild. So the first one was from a group studying Boyajian star. And the claim was that the 20% diminution of that star's luminosity was due to someone constructing a megastructure that dimmed the light from the star in a way that was aperiodic, not periodic. And the reason it was not periodic is because that structure was under construction. So various pieces blocked the light from the star at various times. All right, that was one claim. Next, we got a claim from Bora and Tarter looking at data from Palomar Sky Survey. And they claimed that there were 234 stars, which were each emitting a very short pulse, right? So 234 alien technologies out there. And lastly, there came out of the Rattan 600 telescope a claim of a signal that was very much like what they would expect from a narrowband transmitter on the sky. And it did not repeat. Nevertheless, this was a field day for the press. They loved it. And it was a pain in the butt for us in the community because it took a lot of our time to try and disabuse the public and the media of these being really good detections. And the fact that we could say with the Rio scale that it was a very low probability of being valid didn't help because nobody was really tuned in to using that scale. So ET was the wrong answer for those claims in 2016. The better answers are Boyajian's star being surrounded by dust. We now have enough multi-wavelength observations so that that dust can be characterized, right? The Bora and Tarter pulses, Michael Hipke very cleverly showed that these were a processing artifact, right? And due to the fact that the absorption lines in the stellar spectra, these 234 stars, are not randomly spaced. And so if you Fourier transform things enough times, you're going to get an artifact. And he demonstrated that beautifully. And lastly, the Rattan 600 RFI turned out to be a military classified satellite. To the best of our knowledge, that's the explanation for that. So Rio didn't work. The Rio scale didn't work in 2016. So we went back to the drawing board to produce Rio 2.0. The thing that was problem with the Rio scale as originally conceived is we were being asked to answer questions that you actually wouldn't know the answer to from the nature of the data, such as, is this signal intended for Earth specifically, or is it just leakage? The scale still runs from 0 to 10. It's an interactive calculator that you can get on GitHub, and 0 is still the most important number on that scale. So we will try and get some traction in the community to get people used to thinking about the Rio 2.0 scale. And there are a number of other things you can do in terms of how you observe in the future that can help to build confidence, particularly for transient signals. So the gold standard is simultaneous co-observations. So multiple observatories with the appropriate calculations for propagation times between them. Multiple beams within a larger field of view. And it's possible with an array to create offset nulls, to null out. If you're looking with n beams, when you look at beam number n, it's possible to null out all n-1 other beams. So this helps you to eliminate the case where there is a very strong signal coming from the direction of one of those beams, and it's so strong that it spills over into adjacent beams on the sky. So you can null it out. You can also, given predictable catalogs for satellites that will be coming into your field of view and transmitting on frequencies that you're interested in, you can actually null out the satellite path as well. So we've started doing this kind of thing for more modern searches. This is the Veritas array. It's built to find Cherenkov radiation from high energy particles entering the atmospheres. And normally those 500 pixels at the focus of these 4 dishes look for long streaks, long trails. We could actually write some new software that looked for single pixel events, but required that that single pixel in each case be the same pixel on the sky. And so people have been going through archival data, and there's been something like 30 hours of dedicated observing time for optical SETI on this array. The multiple beams improve your confidence, right? The larger number of beams means that RFI is more likely to be seen in multiple beams, while a real source will only be in one or spill over to adjacent beams. And you can see how exponentially that improves with the number of beams that you're putting into your field of view, starting with the 3 that we had at the current ATA. All right. The other thing that you can do is look forward to using an imaging correlator if you're working at an array. So you take the total power incoherently summed out of each of your antennas, and you trigger on that total power. And then you do your correlation on those events above threshold in order to gain spatial localization. And you note that interference doesn't correlate to form an image. So we did that experiment with Boyagin's star, and in the Allen telescope array. So we summed the output of the voltages incoherently from all the telescopes from 1 to 10 gigahertz. Then we applied a threshold. And for each of the events above threshold, we actually imaged the data at that frequency. So here you can see that around 4.35 gigahertz, there was an interesting, strong event, and our calibrator just behaved normally. So we made an image with the calibrator data at 4.35 gigahertz and with the interesting SETI data. So here's what happened. The calibrator imaged beautifully to a beam pattern, and the data at 4.35 gigahertz from the source didn't correlate at all. It is interference. And so this is a pretty robust way of excluding interference, but it's special cases. It requires a correlator, which fortunately, an array with a correlator, which fortunately we have access to. So the co-observation strategies, there's lots of opportunities for SETI in the radio to collaborate with pairs of antennas. And then, as I've already said, we're really looking forward to this cosmic spigot on the JVLA, and then thinking about the future with the NGVLA. And of course, this commensal spigot can be used. We'll build it, we'll use it for our SETI observations, but another spigot could also be built that could be used by the astronomical community for many other special searches. So in the optical, we're having to build our own detectors because this high time resolution, which we think is important for engineered signals, is not really available at many observatories. So here you see Shelley Wright from UC San Diego looking through a 1 meter plastic Fresnel lens. Now imagine building a Buckminster Fuller type dome structure with that Fresnel lens in each hexagon, and that is focusing a large area of the sky down onto a very sensitive detector. So with 126 such Fresnel lenses, you can see 10,000 square degrees of the sky instantaneously. And remember, you need to build 2 domes about 1 kilometer apart. And that's what's happening at Palomar, interrupted by COVID. But it will get there, and it's going to be exciting. There's another project that's trying to observe not just 10,000 degrees, but all of the sky, all of the time. Oh, I'm sorry, here are engineering prototypes of the PanoSETI that were installed at Lick just before everything shut down. So they've been getting some engineering test data for a long time with this. This is the other project that wants to look not just at 10,000 square degrees, but it wants to look at all the sky all the time, right? And it uses astronomical grade cameras with wide angle views, gratings, and fast readout, fast time readout of those cameras in order to look at the sky and look for this kind of pattern. So thermal objects, well, they'll be dispersed in the spectrum, so you'll have 0 order and the higher orders, but monochromatic laser signals, such as might be used for the equivalent of breakthrough starshot to accelerate a sail, those will show up as just 2 points. There will not be this dispersion. So the first of these has been installed at the Ferguson Observatory in Northern California, Sonoma. And you can see that the sky doesn't look as nice and pristine as that, but indeed software can sort through all of those events and look for these monochromatic laser pulses. Now, the second installation is actually just on a boat yesterday heading to Haleakala, right, in Hawaii. And so that will form a long distance pair for yet more discrimination and verification. And if we can build a dozen, maybe we need as many as 15 of these camera sites around the world, then you will actually be looking at all the sky all the time. And who knows what might be there that we haven't seen before, because we haven't looked at the optical sky in this way. So, principle number 8, we have still no idea how to achieve such a consensus. We've held meetings at AAAS, we've held sessions at AAAS meetings, trying to explore what body, global, could in fact perhaps have the ability to go searching for consensus across the globe. No good ideas, sorry. And finally, we had that SETI permanent committee under the auspices of the International Academy of Astronautics. And so perhaps we're suggesting to the astrobiology community, who is going to be looking for biosignatures, just as we've been looking for technosignatures, that maybe such a committee should be constructed perhaps within COSPAR, so that we can think about what are required in order to make the claim of the detection of a biosignature or life beyond Earth. And that is the end.
Thanks very much, systematically walking us through the steps before making big claims. So I'll start with one question. You mentioned that we should have different hardware systems to allow verification. Should this just be the backends, or do you think receivers or antennas could cause issues of spurious signals too?
Yes, you can get spurious signals from your receivers, yes. So that is why you want hardware you didn't build as part of this verification. The other thing that I didn't mention, but it's inherent, is that unlike many other scientific explorations, this endeavor is just rife for people trying to commit deliberate hoaxes. We've seen it in the past, and we'll no doubt see it in the future. So exactly what your second telescope for verification is going to be, I just assume that that was somewhat close kept, that indeed you have a cadre of opportunities and telescopes that you might use for validation, so that instead of just hoaxing one telescope or two telescopes, to be successful as a deliberate hoax, it would require messing around with a whole lot of different telescopes. So I don't know. I don't know how we get around this attractive nuisance aspect of searching for technosignatures. But having a stable of telescopes that are willing to give you a little bit of director's discretionary time to do this verification on call is the best we can do.
Thanks, Jill. Some years ago at the SETI at 50 meeting in Green Bank, Judge Tatel asked the community whether we had a Tiger team in place to inform the US president of an actual detection. During the discussion, he also said something like, "This is far too important to involve the UN." Do you have comments on this?
Well, when we were a NASA project, right, we actually had, we had in our post-detection protocol, we had to name the AA at NASA who would be the one to inform the executive branch, right? We don't have that now. And the idea of sending the IAU telegram, or an ATEL, is really to fortify the professional response to this. So the media are not going to be able to call up the Discovery site and say, "Tell me what you found," right? They're just going to get swamped. But if you have astronomers forewarned by this ATEL or IAU telegram in advance, where they've seen the Discovery data, they can interpret for their local media what's going on, and how significant it is and how much attention should be paid to it. That was our best attempt to do this sort of tiger team globally.
Okay. Do you have any comments on IR access signature searches for techno signatures?
Yes, there have been a number of them. The first one was by Kerrigan, who looked, and it's hard. It really takes a lot of data to distinguish the difference between something that might be the backside of a megastructure and a debris disk. So it isn't a one-off easy distinction, but it can, it can be done. And so Jason Wright and his students did this big GHAT project using the data from the WISE spacecraft, which made an infrared survey of the entire sky. And they went looking for Kardashev type 3 civilizations, the entities that had the ability to manipulate the power from all of their galaxy. And they found a couple of interesting objects that have shown up that have then been put on exotical lists for observation. And then they're doing now the harder investigation, which looks for type 2 Kardashev civilizations, where you're looking for something that can manipulate the total power output of their host star. That's a much more, field is much more confused and more difficult to do that. But they are working on it.
Yeah. So
yeah, I mean, SETI can be archival as well as observational.
Could you imagine getting the prominent science journals, example, Nature, Science, APJ, etc., to agree to the creation of an independent review committee of multiple experts that would review articles of potential astrobiological or SETI relevance in lieu of the typical process of review by just 1 to 3 select scientists? This might keep the authors less sensationalistic in their claims and provide the journals better confidence in the true quality and impact of the article.
I think it's a really good suggestion, and I'm not aware of anybody who's trying to do that. But certainly we can have a conversation and begin to talk to some of the editors to see if they think that's reasonable. Thank you for the suggestion.
If it exists, what is a formal protocol for retracting what is believed to be the discovery of a SETI signal, but later turns out to be explained by some other astrophysical mechanism? Furthermore, how do we prevent or at least minimize mass hysteria a la Orson Welles' War of the Worlds?
Well, there have been a number of conferences, roughly called Societal Impacts of SETI, that look into the potential for panic a la Orson Welles. And in general, they find it's not there. Too many people already believe in ET, and many of them believe that they're here right now. And the world is much better connected than it was back in the Orson Welles episode. So what was, Sri, remind me
the first part of the question is, what is a formal protocol for retracting what is, a claim after it turns out some analysis, some subtle astronomical signature?
Well, start with giving it a Rio 2.0 scale ranking of 0. And I think there you just, first of all, it's SETI, it's sensational. You're not going to pull it back out of the ether. It's going to be there, but what you need to do is provide a good paper that presents the evidence for explaining this and make that available, and make sure that the same, perhaps, Tiger team or committee or the same astronomers to whom you've sent this ATEL all have that information and can use it when asked. But you're never going to pull it back. I mean, we still talk about the wow signal, which literally, if I had been running that program, you would never have heard about that because it did not pass the verification and procedures that the astronomers who built the observatory set up for it. I mean, there were two beams, east and west, and a valid candidate had to show up in the east and then show up in the west. And this wow signal showed up in one or the other, we don't know which, and was never seen again. So I would have given that a 0. But it was strong, it was exciting. So it's become part of the folklore.
How problematic are projects like Starlink or the onset of microsatellites to the SETI effort? Are these just nuisances and easily identified or serious conflicts?
Well, just as for all optical astronomy and radio astronomy, they are a pretty big nuisance. I mean, Tony Beasley is working hard to represent the radio astronomical community in discussions about these kinds of things and how we can best mitigate and can we get them to switch off when they're over or within the field of view of an observatory, or what other mitigating circumstances can we see? I mean, right now, there are all kinds of out-of-band and spurious emissions from these spacecraft because it costs money to put in robust filtering, and they won't do it unless they won't practice the spectral hygiene unless their competitors force them to. So first of all, clean up the emissions, and secondly, see how we can mitigate their presence above an observing site and not lose that whole band of sky.
It seems like an array that monitors the entire sky would also be useful for detection of brief astrophysical transients. Are there plans to make the data collected open access?
Yes, yes. And there are also, there are already collaborations between PanoSETI and Laser SETI and astronomical observers.
Any suggestions for how radio amateurs can participate? Many, parentheses, hundreds to thousands amateurs now have sensitive receivers, and some have 1 to 10 meter dishes, and the narrowband spectrometers are available at low cost. A way to coordinate these observations to mitigate RFI is needed.
Yeah, I'm just now blanking on the organization. Oh, SETI League, right? The SETI League has tried for decades to coordinate amateur observers and worked with the Amateur Radio Astronomy Association to do this. I don't think they've been very successful, but it's at least a start of a place where either SETI League or Sarah could take this on as a function. How do we get amateur radio astronomers coordinated in an observing campaign mode or continuous observational mode? There have been over in Japan, there have been some coordinated campaigns that last, for a night or two, but not continuous coordination.
In the optical world, there's a very venerable organization, the AAVSO,
Right.
and they've done a fantastic job of both harnessing the public enthusiasm for the night sky. I mean, many of the amateur astronomers are actually out there, looking for sky pollution issues. And also the AAVSO really is actually allows professional astronomers really amazing data, especially on variable stars. So something of that sort in radio would be very useful.
Well, that's what Sarah is trying to be, the Society for Amateur Radio Astronomy.
You mentioned data being taken simultaneously with the WIDAR VLA. Is this the same or expanded upon from what is being done at the GBT? Without any detections from the work so far with GBT, how do they enable justifying going further with attaching these backends on the VLA antenna? Okay, that's a bit sharp question. So I'm sure you'll have a good answer.
Yes, commensal observations have been done with the GBT, the breakthrough backend system, as well as dedicated observations. And the question I would raise is, why not, right? If you could be on the sky 24/7 with a commensal backend, looking in places that the GBT hasn't looked, right? At frequencies the GBT may not have covered. It seems to me that it's worth doing. I mean, yep. when we historically, right, astronomers have this great history that when you build a new instrument, you go to your funding agencies and you say it's going to solve question A and question B and question C. And inevitably, the best thing it does is show you something you didn't expect. So why wouldn't you be trying to survey the sky?
Yeah, I'd like to add as a different plug for commensality is it so happened that the radio astronomers, sort of doing more routine radio astronomy through archival analysis found the first fast radio burst, which has launched a whole new industry in radio astronomy and is completely influencing the design of future telescopes. In fact, CHIME rose to great prominence, I would say, thanks to FRBs than the original purpose. Now, it could well have been that one of these SETI radio searchers could have found them, okay, because there have been discussions of looking for negatively dispersed signals as a way of techno-signature. That certainly would be a techno-signature that would be, I would say, almost infallible, at least in my opinion. So I don't think there's a either or issue here, Jill. I completely agree with you. If resources can be found and if a serious commensal search is done, there may be benefits at no cost to additional observing time. And in fact, my hope is that with the optical SETI, which I'd only kept a track of, they may be the first ones to end up finding fast optical bursts, a whole new phenomena. Mm-hmm. In which case, that would be a celebration of commensal research.
Yes, yeah.
What is the current status of the ATA?
The ATA is undergoing refurbishment now. So we are building the second generation of very wideband feeds called Antonio feeds, because Franklin Antonio is the person who is providing the funding for this. And they operate over 1 to about 12 gigahertz simultaneously. And they worked in the past, but they were not robust, right? We kept breaking solder joints at the tips of these wideband feeds. So they have been overhauled significantly and are being, new feeds are being put on the telescopes. And the back-end structures, the signal processing, we've ripped out all of the 3 beamforming equipment that we had and the correlator. And so a new correlator beamformer is being built based on the kinds of things that Breakthrough Listen has done elsewhere with FPGAs and GPUs. So we have and right now, one of the researchers at the ATA, Wael Farah, is using a number of the dishes for looking for fast radio bursts and has in fact made a detection.
And just today he had an upper limit on this magnetar, which linked FRBs to magnetas, and there's a short burst and there's no commensal or coincident radio signal. So it's pretty clear he's already active. What is the highest radio microwave observing frequency SETI searches target, and why? Is there no interest in millimeter or the sub-millimeter?
Well, certainly there's interest, right? But there is this historical terrestrial microwave window from 1 to 10 gigahertz. So frequencies lower than 1, you're getting synchrotron radiation from the galaxy. Higher than 10, you begin to get emission from oxygen and water vapor. So we've sort of carved out this quiet terrestrial microwave window as our focus. But anyone who has opportunities to use a higher frequency facility and wants to do SETI, that's great. But for systematic exploration right now, we're sticking to the lower frequencies.
What are the lessons learned from BLC1?
Yeah, there are many. And let's just say that nodding on and off is a traditional way of observing in radio astronomy, is not the best way to exclude interference.
Has an effort been made to encourage researchers outside the SETI community itself to use the Rio scale when reporting any anomalous signal, including those for which the authors are not at all trying to make an ET claim? I think this would significantly increase its uptake and would be generally more useful than just reporting the SN ratio.
Yes, and I don't know how to do any more of that encouragement than we have been currently doing, which is giving papers about it, bringing it up, right? Asking, okay, what's the Rio 2.0 number on that detection or claim detection? Getting the media to ask when they interact with researchers who are making a claim, what's the Rio 2.0 number that you're assigning to this discovery? It's education.
Which you already have educated nearly 100 people today on the Rio scale, which I was not aware of. So at least you got one new convert. Thanks very much.